Tonight, a simple law of motion is supposed to keep you safe. Objects keep going, gravity guides them, dust and ice obey. Dr. Michio Kaku has repeated the same quadratic distinction for years. The difference between a rock and a spacecraft is the ability to change momentum. Delta V, nature does not carry brakes. And yet in the early hours of today, the tracking stream looks as if someone pressed one. A deep space network timestamp, clean and indifferent, marks a deceleration for 3I Atlas that should not exist in a natural body. 15 kilometers per second removed from its path. Not a gentle drift, not the slow bleeding of speed over months, but a sudden subtraction. If that number is real, then 3I Atlas did something even comets do not do. It refused to keep falling forward. On paper, the official language stays calm. Further analysis required. Data under review. No conclusions at this time. NASA and ESA style caution, as careful as a nurse turning down the lights. But another kind of record travels in the margins, in the way engineers speak when they think no one is listening. Cross-check requests, independent ranging, a note to compare tracks from separate antennas. And one line that does not belong in ordinary astronomy. The object entered a stationary solution, a phrase normally reserved for deliberate station keeping. If that phrase is accurate, then 3I Atlas did not merely pass through our system. It selected a place to pause. Here, we move slowly, the way a calm mind moves through a dark room. If you enjoy these long, quiet investigations, you can support them by subscribing, leaving a thoughtful comment, and sharing what you think this object is or what you hope it is not. Your theories help shape what we explore next, and your presence turns the silence into a community. Now, dim the lights. The first page of our file tonight is not speculation, it is measurement. Fear grows best in vagueness, and the antidote is always the same: numbers, patiently earned. The headline figure has already leaked into rumor, dressed in dramatic clothing, but it has a plain scientific form: 33 billion tons, 3.3 but 13 kilograms. A mass so large it stops feeling like a thing and starts feeling like geography. Dr. Michio Kaku often returns to a simple point when he talks about advanced civilizations. If you want to move big objects, you begin with control. You learn how to push and pull on forces the cosmos offers for free: gravity, magnetism, radiation pressure. To a restless mind, that sounds like starships. To a sleepy mind, it sounds like a warning. If something can change momentum at will, it can choose when to arrive and where to wait. So how do you weigh something you cannot touch? You watch what it does to what you can touch. That is why the name LAGEOS-2 appears so often in this story. LAGEOS-2 is not a telescope. It is a passive satellite, a dense sphere covered in retroreflectors, built so its orbit can be measured with extraordinary precision by laser ranging. It is, in a way, a bead on a string. When gravity changes, the bead slides, and the slide can be read in millimeters. In a quiet solar system, LAGEOS-2 follows a path that can be modeled with near-obsessive detail. Earth's slight bulge, the tug of the moon, the pull of the sun, the faint pressure of sunlight, even subtle atmospheric effects. All of it is accounted for. That is why a small mismatch matters. When the residuals do not settle down, you do not jump to fantasy. You ask what mass was missing from the model. The rumor version of the calculation says it like a spell. LAGEOS-2 drifted Therefore, 3I Atlas weighs 33 billion tons. The sober version is less theatrical and more unsettling. A mass placed somewhere near the Earth-Sun line changes the gravitational potential in a way that slightly reshapes orbits. It is not a shove you feel in your chest. It is a whisper inside equations. Analysts subtract everything they can name, then test what sort of intruder could explain what remains. The file keeps circling one location where that intruder makes the most sense. Lagrange Point L1. L1 is a balance point between Earth and the Sun, a shallow gravitational saddle where a spacecraft can maintain a stable vantage with small adjustments. We use it for observation and warning. We put monitors there. So when a mass solution repeatedly points toward L1, the mind begins to taste intent, not because L1 is mystical, but because it is strategic. Now, the number itself deserves respect. 3.3 raised to the 10 or 13 kilograms is not a casual rock. It is a mountain's worth of mass, concentrated into something that the early optical story does not quite match. That is the first friction point. A natural body with that much mass should also have a size that tells on it. It should scatter light more loudly. It should vent, fracture, glow, or trail dust in an honest way. But in this file, the brightness and behavior rid muted, as if 3I Atlas wears an outer skin meant to look like ordinary debris while hiding a far denser core underneath. This is where responsible doubt tries to keep us warm. Perhaps the LAGEOS-2 residuals are a modeling error. Perhaps the Deep Space Network deceleration is a corrupted track. Perhaps multiple small perturbations, stacked just right, mimic one heavy visitor. These are good thoughts. They are how science protects itself from stories. But the file keeps returning to the same uneasy convergence, a sudden deceleration of 15 kilometers per second, a mass estimate near 33 billion tons, and a solution that wants the object to be hovering near Earth-Sun L1. Dr. Avi Loeb has argued, calmly and repeatedly, that we should remain open to the possibility that some interstellar visitors are technological, and that subtle propulsion can masquerade as natural motion. Dr. Michio Kaku has described how a civilization that can manipulate planetary scale energy might use magnetism, radiation pressure, and engineered materials to do what looks impossible. We do not need invented quotes to feel the weight of that idea. We only need to notice how stopping is not an accident of gravity. It is a decision written in motion. Imagine, only for a moment, what the title suggests. An alpha fragment that enters our neighborhood fast, then sheds speed as if shedding a coat. The outer layer peels away, not with an explosion, but with a controlled release, exposing a core that is black, cold, and much too heavy for its apparent size. Then let the image soften again, because our task tonight is not to panic. It is to place one careful question on the table and leave it there like a stone. If 3I Atlas truly carries 33 billion tons, what is it made of, and what kind of mind would build such a thing? And that is where we turn next. If the mass is real, and the silence is real, then the material has to be real too. In the next chapter, we will listen to the physics of density and strength, and ask what sort of solid could wear the mask of a fragment while holding the weight of a mountain. If the mass is real, then the next mystery is quiet and physical. Not who sent 3I Atlas, but what it is made of, because weight demands structure, and structure always leaves fingerprints. The file opens with numbers and closes with a feeling. LAGEOS-2 suggests a hidden load of 3.3 was 10 to 13 kilograms, and the Deep Space Network logs suggest a motion change that should have shattered any ordinary comet. Put those together, and you are left with a simple need. Whatever 3I Atlas is, it must be strong enough to stay whole while the universe tries to tear it apart. Dr. Michio Kaku often frames interstellar travel as a materials problem before it is a fuel problem. You can imagine engines, but first you need something that does not crack under vibration, does not boil off in sunlight, does not crumble into dust after one hard maneuver. In that sense, solid-state physics becomes more unsettling than propulsion. It asks whether the object's quietness is not a lack of activity, but a sign of refinement. We can anchor ourselves with a few calm facts. Typical rock is around 3 grams per cubic centimeter. Iron is about 8. The densest stable element we can name, osmium, is around 23. Those numbers feel heavy until you compare them to what gravity can do in the deep universe. White dwarf matter and neutron star matter can reach densities that make chemistry irrelevant, but they only stay that way under crushing pressure. Outside those prisons, such matter would not remain politely solid. That is why the size matters. Brightness is not a ruler, it is a guess. Astronomers infer size from how much sunlight an object reflects, but that inference depends on surface reflectivity, shape, rotation, and dust. If 3I Atlas wears a surface that is unusually dark, it could be larger than it looks. A larger body would bring the average density back toward the familiar, letting the mass be just a very big, very compact intruder. And unusually dark surfaces are not fantasy. On Earth, carbon-based microstructures can trap light so efficiently they look like holes cut into reality. In space, a surface built to swallow sunlight would also manage heat differently than bright ice. It can absorb, distribute, and radiate energy in a controlled way, reducing the hot spots that trigger cracking and outgassing. A body that is big, black, and thermally disciplined can hide in plain sight, not by being invisible, but by being uninteresting to quick optical surveys, especially if it rotates slowly and offers little reflective edge. But the file does not let us rest there. Even a generous correction does not erase the tension between behavior and expectation. Big natural bodies are usually messy. They vent, they shed, they spin rubble into halos. If 3I Atlas carried 33 billion tons in a loose pile, the Deep Space Network would not have seen a clean change in momentum. It would have seen disintegration, a slow blooming cloud, a confession written in fragments. So the next hypothesis becomes architectural. A layered object can cheat our instincts. An outer skin of dust and grit can mimic a natural fragment. Beneath it, a rigid skeleton can hold shape through shock. Inside that, a ballast core can supply mass without requiring exotic physics. Tungsten is dense and stubborn. High-temperature superalloys can keep strength when ordinary metals soften. Metallic glasses and advanced ceramics can resist crack growth by spreading stress instead of concentrating it at a single crack tip, the place where fractures usually begin. The more you think about it, the more the payload idea becomes a stress test. A sudden force does not only threaten to snap the object in half, it threatens to delaminate layers, to heat one region faster than another, to make materials expand at different rates and tear themselves apart. If 3I Atlas stayed coherent, then either the maneuver was gentler over longer time than it first appears, or the structure was built to survive differential expansion, vibration, and radiation damage without fatigue. This is where Dr. Avi Loeb's method becomes useful. He argues that when an interstellar visitor behaves oddly, we should test technological interpretations without romanticizing them. Do the simplest engineered story fit the measurements? In this story, the simplest engineered story is not a sleek craft with windows. It is a blunt object designed to survive. A mass that can take heat, cold, radiation, and sudden forces and still remain one piece. If you picture it, do it gently. Picture 3i Atlas as a black instrument case floating in a bright room. The surface is matte, light drinking, almost featureless. The comet-like dust is only a disguise that can be stripped away when it is no longer needed. Under the disguise, structural ribs cross like the inside of a vault, turning impact and acceleration into distributed strain. The core is heavy on purpose, a gravity anchor, a handle the universe cannot ignore. And then the story takes one step into the darker corridor, not as a claim, but as a boundary marker. What if the density is still too high? What if even a large ultra-black body cannot reconcile the mass and the apparent cross-section? Then we are forced to whisper words that physics allows, but engineering does not yet possess. Degenerate matter in containment, or even a micro-black hole used as ballast and power. These ideas are not conclusions. They are what your mind invents when the numbers refuse to fit inside our comfortable catalog of materials. The unsettling comfort is that extreme mass does not need to move to be meaningful. It changes its neighborhood by existing. It makes orbits drift by millimeters. It makes station keeping expensive for anything else nearby. It can serve as an anchor for fields, sails, or sensors. In Dr. Michio Kaku's language, advanced technology often looks like control at rest, not fireworks in motion. So we end this chapter with one calm question, sharp enough to stay with you, but soft enough to let your breathing slow. If 3i Atlas is built from supermaterials and deliberate architecture, what was the builder protecting? The payload from space or space from the payload? In the next chapter, we follow the moment where matter and motion meet, the braking maneuver itself, and the two ideas that keep surfacing around it, radiation pressure as a sail and magnetism as a silent brake. Tonight, December 15th, this story goes public while most of the world is still busy with ordinary life. Above that ordinary life, the Deep Space Network appears to record something that should not happen. 3i Atlas slows down by about 15 kilometers per second. The line in the tracking file is not poetic. It is a timestamp, a fitted trajectory, and a note that the solution only converges if a large delta V is allowed. No one writes impossible in an engineering log. They write anomalous, then they ask for a second check. But the meaning is the same. A natural fragment should not be able to press a brake pedal. When the same folder also holds LAGEOS-2 residuals, the tension tightens. LAGEOS-2, measured by laser ranging, behaves like a floating test mass for the local gravitational field. If its tiny drifts are being interpreted correctly, they point toward a hidden weight near the Earth-Sun line. The number that keeps returning is 33 billion tons, about 3.3 blah blah to 10 to 13 kilograms. It is the kind of mass you do not encounter, you orbit it. A change in speed is not just a change in speed. It is a change in momentum, and momentum refuses to vanish unless it is handed to something else. For a body with 3.3 quadras or 10 or 13 kilograms, shedding 15,000 meters per second implies an impulse on the order of 5.10 or 17 kilogram meters per second. In energy terms, you are looking at roughly 4 to 10 21 joules. If you insist on translating that into something human, it brushes the scale of nearly 1,000,000 megatons of TNT. The calmest way to say it is also the coldest. Whatever slowed 3i Atlas had to push that cost into the universe somehow. The first place the mind hides is in natural forces. Comets can accelerate slightly as jets of gas vent from their surfaces, and small bodies can drift under sunlight over long spans of time. But those effects live in millimeters per second, sometimes centimeters per second, spread across weeks and months. 15 kilometers per second is not a nudge. If outgassing did that, 3i Atlas would have needed to throw away an absurd fraction of itself as a rocket exhaust, and it would have announced the act with a blinding, messy coma. This is the doorway where Dr. Avi Loeb's favorite question becomes useful, not as an answer, but as a discipline. When an object behaves in a way that natural models struggle to reproduce, we should test technological interpretations without turning them into a fairy tale. One of the simplest non-flame propulsion ideas is also the quietest: a sail. Sunlight carries momentum. Radiation pressure is real. Near Earth's distance from the sun, that pressure is only a few millionths of a Newton per square meter, almost nothing in the language of mountains. For a small, light craft, it is enough. For 33 billion tons, it sounds like a joke until you do the math. To produce a useful deceleration with photons alone, the effective sail area would need to be so vast that it stops feeling like an object and starts feeling like a shadow, a structure measured in planetary scales. And yet the file gives one detail that makes the sail idea harder to dismiss. The deceleration interval is also when the optical behavior changes, as if a dusty exterior begins to peel away. The summary language is careful, but the image is vivid, a shell tearing off under stress. If 3i Atlas carried a disposable cloak of dust and grit to look ordinary, then the moment it braked would also be the moment that cloak became a liability. A controlled maneuver can strip camouflage. It can also reveal hardware that was folded and hidden until it was needed. Dr. Michio Kaku has often emphasized that advanced civilizations, especially Type 1 on the Kardashev scale, are defined less by fireworks and more by control of fundamental forces. In that framing, braking does not require a plume if you can interface with the environment itself. Space is not empty. The solar wind is a river of charged particles threaded by magnetic fields. A magnetic sail, sometimes called a magsail, could push against that river by generating a field that deflects the plasma, transferring momentum to the wind instead of carrying reaction mass. This is where the two ideas can join into a single, unsettling mechanism. A dark, photon-absorbing structure can harvest radiation pressure and manage heat. A strong magnetic system can couple to the solar wind and multiply the effective area of interaction far beyond any physical sheet. The sail touches light. The field touches plasma. Neither needs to glow. Neither needs to scream. Both can work in the quiet way that makes the mind feel watched, because the universe itself becomes the reaction mass. There is a grounded speculation tucked into the margins that fits the Michio Kaku style of use what is already there. If 3i Atlas is able to store energy, then a pass through a dense magnetized environment could charge the system like a slow cosmic capacitor. Jupiter's magnetosphere is one such environment, a vast region filled with plasma and powerful fields. Some analysts whisper that Jupiter may have been used not as a destination, but as a charging station, a place to load the brake before the braking was revealed. One page of the file looks like it has been handled too many times. It references a local disturbance in the solar environment during the same interval, the kind of phrasing used when instruments notice that the wind itself is being shaped. The ordinary explanation is solar activity, a coronal hole or a transient event that makes the data messy. The less ordinary interpretation is that 3i Atlas shaped the mess, creating a corridor of altered plasma that made braking and later station keeping easier. Dr. Avi Loeb has explored how subtle interactions with the space environment can produce effects that look puzzling if you assume every visitor is passive. If you want one imaginative image to carry into sleep, let it be gentle and specific. Picture the solar wind flowing past the Earth like a thin, invisible fog of charged grains. Now place 3i Atlas in that flow, not with a visible net, but with an invisible bowl. Particles curve, field lines bocos bend. A wake forms that is not dust, not gas, but a quiet rearrangement of the space around it. The object does not fight the cosmos. It persuades the cosmos to take the momentum it no longer wants, and then after persuasion comes the stillness. The track solutions begin to prefer the Earth-Sun balance point, Lagrange Point L1, the shallow saddle where a careful system can hover with minimal effort. That is not where a random fragment ends up by accident after a massive, clean deceleration. It is where you park something you want to keep steady. It is where we park our own sentinels, because from L1 you can watch the sun and the Earth at the same time. If 3i Atlas is sliding into that region after shedding 15 kilometers per second, then the braking maneuver was not an escape. It was a parking maneuver. So the question we leave resting beside the numbers is quiet but sharp. If a 33 billion ton object can arrive, brake, and hold itself near Lagrange Point L1 using sails of light and fields of magnetism, what does it plan to do with the advantage of patience? And why did it choose to stop close enough for the Deep Space Network and LAGEOS-2 to notice? In the next section, we follow the orbit it appears to prefer and the strange intimacy of a parking spot between Earth and the Sun, where silence can be strategic. Tonight, the story stops being about speed and starts being about location. Because if 3i Atlas truly slows and then parks, the most frightening detail is not the braking. It is the choice of where to become still. There is a reason engineers speak about Lagrange points with the same calm respect sailors give to currents. Earth and the Sun pull on everything all the time. Most places in between are not resting places, they are slopes. But a few rare locations feel almost level, like a shallow saddle carved into gravity itself. Earth-Sun L1 is one of those places. It sits roughly 1.5 million kilometers from Earth toward the Sun, close enough to be part of our neighborhood, far enough to feel like deep space. In the rotating frame of the Earth-Sun system, the outward centrifugal tendency balances the combined pull in a way that allows an object to hover with relatively small corrections. We already use L1 the way we use a lookout tower. Solar observatories and space weather sentinels have lived there for decades, because from that vantage, you can watch the sun continuously and sample the solar wind before it reaches Earth. NASA and ESA place instruments there to measure storms while they are still upstream, giving us time to prepare for the invisible weather that can rattle satellites and power grids. This is why the folder feels different when it starts pointing to L1. A random fragment does not naturally end up there and remain neatly placed. L1 is not a true sink, like a planet's gravity well. It is more like a ridgeline. It is delicately unstable. Without station keeping, objects drift away. So, when the Deep Space Network solutions keep converging on L1 as the resting region for 3I Atlas, the implication is gentle and terrible. Something is holding it there. In the language of orbital mechanics, you do not sit exactly on L1 like a pin on a map. You move around it in looping paths called halo or lysogyous orbits, wide, slow figure eights that keep the sun and Earth in view. Our own spacecraft do this, constantly making tiny course corrections. The motion is graceful, but it is not accidental. It is maintenance. Dr. Michio Kaku often talks about advanced civilizations in terms of infrastructure, not vehicles. The kind of civilization that can manage planetary energy would naturally value places like L1 because they are leverage points. From L1, you can monitor, intercept, and influence the flow of sunlight and plasma before it touches a world. Even if you never touch the planet itself, you can still touch what the planet receives. Dr. Avi Loeb has also pointed to a quiet logic that does not require sensational assumptions. If probes existed, if any artificial visitor wanted to observe without landing, it would choose the simplest parking spaces nature provides. Lagrange points are exactly that, gravitational shelves where you can linger with minimal fuel and maximum visibility. Now return to our specific intruder, 3I Atlas. A 33 billion ton mass at L1 is not just a visitor. It is a new feature in the local gravitational landscape. Not a new planet, not even close, but a concentrated weight placed where our own monitoring systems are already staring. That is why the file reads like a conversation between instruments. LAGEOS-2 whispers through residuals. The Deep Space Network answers with ranging and Doppler. The sky becomes a lab bench, and the psychology of the location matters. L1 is between Earth and the Sun. It is always lit, always exposed to solar wind, always in line of sight for communication. If 3I Atlas wanted to be found, L1 is theatrical. If it wanted to watch without being found, L1 is reckless. So the stillness there does not feel like hiding. It feels like permission. There is another reason the choice is unsettling. From L1, you can see Earth as a whole, a single rotating system of weather, oceans, and lights. You can watch the night side bloom and fade. You can measure the atmosphere as it breathes. You can listen to radio leakage with clean geometry. If you were patient, you would not need to land to learn a great deal. And yet, the most practical reason to choose L1 might be the least dramatic. It might simply be the easiest place to do the next thing. In orbital design, you choose staging points, you choose corridors, where small changes have large consequences. If 3I Atlas arrived with a plan that includes releasing something, sampling something, or deploying something, L1 is a calm staging platform. Somewhere in the file, a phrase repeats in different handwriting, station-keeping signature. It is not proof. It is not a confession. It is a pattern, the way a heart monitor shows that a patient is not only alive, but being regulated. A natural object drifts. A regulated object returns to its preferred geometry. So we end this chapter with a question that is simple enough to hold in your mind without tightening your chest. If 3I Atlas is holding itself near Earth-Sun L1, then it has either chosen to watch the Sun or chosen to watch Earth. Which one would be more useful to a mind that arrived from interstellar dark and decided, at last, to stop? When you look toward the Sun, you are not looking at a lamp. You are looking at an ocean of plasma, threaded with magnetic lines that twist, knot, and sometimes open like doors. Since 3I Atlas appears to be holding near Earth-Sun L1, every solar monitor that watches upstream becomes part of the story. That is the strange intimacy of this location. L1 is where we keep our early warning eyes, sampling the solar wind before it reaches Earth. If something unusual happens near L1, we do not just see the object, we see the environment around it, like ripples revealing a hidden hull. The folder we are following tonight keeps returning to a second anomaly that arrives alongside the first. The first is motion. Deep Space Network tracking that implies 3I Atlas shed about 15 kilometers per second. The second is weather, a brief, localized change in the solar wind and magnetic field structure that does not fit the usual rhythm of solar activity. The words in the file are careful, transient, uncertain attribution, possibly coincident, but the timing is what makes the mind linger. A coronal hole in real solar physics is not a literal hole. It is a region where the sun's magnetic field opens outward, allowing plasma to escape more freely, often producing faster solar wind streams. They are usually mapped in ultraviolet and X-ray images as darker patches, and they can persist for days or weeks. They are part of the sun's natural breathing. Nothing about that requires aliens. Nothing about that requires panic. And yet, the suspicious phrase that appears in the simulated summary, the artificial coronal hole, is less about a picture and more about a mechanism. It suggests a short-lived opening or channel in the local magnetic topology, created not by the sun alone, but by an intruder that can shape fields the way a hand shapes water. In the calmest interpretation, the data simply show a patch of faster wind and a shift in magnetic direction that happened to coincide with 3I Atlas breaking. In the darker interpretation, the coincidence is the point. This is where Dr. Avi Loeb's style of reasoning becomes an anchor. If radiation pressure and plasma flow can provide gentle forces, then an object that wants to remain near L1 does not need to carry endless fuel. It needs to couple to what is already there: light, charged particles, magnetic fields. Loeb has argued in other contexts that we should take seriously the idea that subtle propulsion can look like natural drift if we are not prepared to measure it properly. Now add Dr. Michio Kaku's broader framing about Type 1 technology. Kaku often describes advanced civilizations as masters of energy and fields, not just chemistry and fire. In that framing, the sun is not just a star. It is a power source and a medium, a place where magnetic structures can be used the way we use wires, coils, and transformers. If 3I Atlas carries 33 billion tons, about 3.3 × 10^13 kilograms, then any method of station keeping has to be clever. It has to be quiet. It has to offload momentum into something larger than itself. So imagine a grounded physical possibility. A strong magnetic system around 3I Atlas interacts with the solar wind, deflecting charged particles and creating a wake that instruments interpret as a change in the local field and flow. You do not need to pierce the sun to do this. You only need to reshape the stream between the sun and earth, like placing a magnet in flowing plasma. The result could resemble, on a small scale and for a short duration, the signature we associate with open field regions, a corridor of altered solar wind that behaves like a temporary channel. If that corridor exists, it does more than look strange. It becomes useful. It can provide a steady push or a steady constraint, a way to lean against the solar wind with magnetic pressure, the way a sail leans against air. It can also provide power indirectly, not as free electricity falling from the sky, but as a controlled interaction where fields and particles exchange energy in predictable ways. A system that can manage that interaction could pay for its position at L1 without obvious propellant plumes. This is the kind of idea that feels like cosmic horror precisely because it is mundane in its logic. Not lasers, not explosions, just a heavy object that can negotiate with its environment. It arrives fast, breaks hard, then settles into a place where our own solar sentinels keep watching, and it holds itself there by using the star as a backdrop for engineering. Of course, the skeptical mind keeps a hand on the doorframe. Solar wind is turbulent. Magnetic fields flip. Coronal holes and fast streams happen. Instruments can be biased by geometry, calibration, or the simple fact that space is messy. It is possible the solar disturbance is unrelated, a natural fluctuation that happened to occur while we were staring at 3I Atlas. In science, coincidence is common and meaning is expensive. But the file has one more detail that refuses to be completely soothed. The disturbance appears aligned with the same Earth-Sun line that defines L1, as if the space between Earth and the Sun briefly became more structured than usual. When LAGEOS-2 hints at a hidden mass, and the Deep Space Network hints at a deliberate delta 5, and the solar wind hints at a corridor, the pattern begins to look less like noise and more like a system exercising control. Here is one imaginative leap, offered softly, then set back down. Picture 3I Atlas as an anchor dropped into a river of charged particles. Around it, an invisible field unfolds, not wide like a planet, but wide enough to matter. The solar wind curves around that field, and the curved flow becomes both camouflage and engine. From far away, we call it solar weather. From nearby, it behaves like infrastructure. So the question we carry forward is not whether the sun can produce coronal holes. It can. The question is whether 3I Atlas can produce something that looks like one, briefly and locally, for a purpose. If it can open a channel in the solar wind to hold itself steady at L1, what else could it open when it decides the waiting is over? If you want the most peaceful definition of fear, it is this. A new capability enters your neighborhood, and it does not announce itself with noise. It announces itself with competence. The numbers we have been holding are not small. A deep space network track that implies 3I Atlas shed about 15 kilometers per second. A mass estimate that circles back to 33 billion tons, about 3.3 close to 10 to the 13 kilograms, suggested by the quiet, millimeter-level honesty of LAGEOS-2 residuals. And now, a location that feels chosen rather than accidental. Earth-Sun L1, a place we use for watching, a place where you do not remain unless you can keep yourself there. This is the moment where Dr. Michio Kaku's favorite scale becomes less like a lecture and more like a mirror. Kaku often uses the Kardashev scale as a way to think about civilizations by the energy they can control. Type 1 is planetary, Type 2 is stellar, Type 3 is galactic. Humanity, in this framing, hovers below Type 1. Depending on the metric, we are something like Type 0.7. We can split atoms and talk across oceans, but we still depend on the weather and the geology and the slow generosity of the sun. So, what does it mean if a mass like this can break and park? Not as a metaphor, as a physics statement. Start with the breaking again, but treat it like an engineering budget instead of a horror scene. A change of 15 kilometers per second for a body with a mass near 3.3 por 10 or 13 kilograms is a momentum shift on the order of 5 por 10 or 17 kilogram meters per second. That momentum does not disappear. It is transferred. Photons can carry some of it. Solar wind particles can carry some of it. Magnetic fields can mediate the exchange. But for a massive object, the interaction must be either enormous in area, enormous in time, or enormous in field strength. If the deceleration occurred quickly, the required forces rise toward absurdity. If the deceleration occurred over longer time, the required forces become more plausible, but the act becomes even more deliberate. Either way, the gesture looks like control. A natural comet does not decide to spend months bleeding speed to arrive at a precise gravitational shelf. A system with a plan might. Now, the station keeping at Earth-Sun L1 adds a second layer. L1 is not a stable sink, it is a balancing act. To hover there, you make corrections. Our spacecraft do it with small thrusters. A heavier object could do it with more subtle means if it can couple to the solar wind and magnetic environment, the way we discussed in the previous chapter. That kind of coupling is not magic. It is plasma physics. But it is also beyond our daily engineering at that scale. This is where Kaku's Type 1 framing bites gently. A Type 1 civilization, in Kaku's storytelling, is one that can manage the energy flows of an entire planet. That does not only mean generating electricity, it means understanding and controlling the environment, weather, oceans, the magnetic field, the distribution of energy in the atmosphere. If a civilization can do that at home, then using magnetic interactions in space would feel like an extension of its daily competence. A Type 2 civilization, in Kaku's framing, can exploit the energy output of a star, not necessarily by building a complete Dyson sphere, but by using stellar energy as a primary resource. If 3i Atlas can borrow from the sun's radiation pressure and borrow from the sun's plasma flow and possibly shape the local field geometry to hold position, then it is practicing a kind of stellar interaction. It does not need to own the sun to use it. It only needs to understand how to lean on it. Dr. Avi Loeb's contribution here is not a scale, but a habit. He reminds us that technology can be subtle and still overwhelming. A sail does not roar. A field does not have to glow. A system that is patient can choose low signature actions. It can use long timescales to keep forces small, and if it does need to do something sudden, it might do it once, accept the stress, and then return to silence. Now let the calm voice carry one unsettling observation. If the mass is truly 33 billion tons, then we are not looking at a probe the way we imagine probes. We are looking at infrastructure. We are looking at something that can change the dynamics of a region by being there. Even if it never fires a beam or releases a craft, it can alter the gravitational and plasma environment around L1. It can complicate our own operations. It can become a permanent variable in our models, a new term in the equations. And if it is infrastructure, then a question appears that feels less like science fiction and more like logistics. What is infrastructure for? It is for sustaining a process, observing, communicating, harvesting, storing, deploying, waiting. The file keeps using the same word in different ways: payload. Dr. Michio Kaku, when he speaks about interstellar travel, sometimes emphasizes that the vehicle is only the carrier. The true purpose is what survives inside. Dr. Avi Loeb, when he speaks about anomalous visitors, often returns to the idea that we should not assume we are seeing the whole system. The visible part might be a shell. The important part might be hidden, dormant, or simply quiet. So here is the thought that makes the room colder without raising the volume. A Type 1 or Type 2 capable system does not need to rush. If it has reached Earth-Sun L1, it has already won the hardest part of the journey. It has arrived with control intact. It can watch for weeks, months, or years. It can wait for geometry, for alignment, for a window, for a signal. It can let us talk ourselves into exhaustion while it spends almost no energy at all. And we, being Type 0.7, do what we always do. We measure, we argue, we publish cautious statements, we reassure, we look for errors, we tell ourselves that the most likely explanation is the natural one, because in science, likelihood is a kind of comfort. But even comfort has to answer to physics. If 3I Atlas really performed a 15 kilometer per second braking and then held near Earth-Sun L1, then the act itself is the message, regardless of who sent it. It says, I can change momentum when I choose. I can hold a position you have learned to use as a lookout. I can be heavier than you can lift and still be quiet. In the next section, the file stops talking about engines and starts talking about surfaces. The shell that peels away, the black core that remains, the package inside the weight. There is a particular kind of dread that arrives when camouflage is no longer necessary, not because something becomes violent, but because it becomes honest. As December 15th moves through the night in the United States, this video goes public, and the story is already changing shape. The early reports frame 3I Atlas like a visitor made of dust and ice, a fragment with a messy halo, a swarm, a smudge, something the brain can place into an old category and forget. But then the breaking happens in the deep space network track, and the mass keeps returning in the LAGEOS-2 residuals, and the category begins to crack. In the simulated file, one phrase repeats with an almost physical feel: the shell peeled off. Not a cinematic explosion, not a dramatic flare, more like a husk separating under stress, the way bark loosens from a tree after a long season of wind. If 3I Atlas really shed about 15 kilometers per second, then any weak layer would have been punished. Differential heating, vibration, tidal stress, the invisible pressure of the solar wind. The kind of forces that do not need to be huge to be persistent. If the outer layer was only there to imitate a natural fragment, this was the moment it became the wrong clothing for the task. We can anchor ourselves again with what we know is plausible in physics. Dust coatings in space are common. Surfaces can accumulate regolith and soot-like carbon from radiation processing. A natural body can look darker over time. A comet can develop crusts, lag deposits, layers of refractory material left behind as volatiles escape. Those are real processes, and in the calm daylight of science, they explain a lot. But the story we are following is not about ordinary darkening. It is about the sudden revelation of something that reads engineered in its silence. A core described as black, smooth, and cold. Not icy, not rubble pile, not porous, not friable. The language shifts from geology to manufacture without anyone saying so outright. This is where solid-state physics returns in a new costume. A shell can be sacrificial. It can be designed to burn off, peel off, flake off, or shed like a stage curtain. In aerospace, heat shields ablate on purpose. In engineering, coatings are chosen to absorb or reflect, to hide or signal, to protect the true structure beneath. If 3I Atlas is a carrier, then an outer swarm of debris could be the simplest disguise. Look like a fragment, look like a messy natural traveler, let the eyes slide away. And when the moment comes to break and park, you let the disguise go. The image is not hard to hold. Picture a broad, uneven cloud around 3I Atlas, grains and chunks in loose company, like a flock that has forgotten its leader. Then, over hours or days, as the trajectory solution shifts and the object stabilizes near Earth-Sun L1, the cloud thins. Not because the sun blew it away in the ordinary sense, but because the system's own choices made the debris irrelevant. Loose material drifts, dense material remains. What stays behind is not a swarm. It is a core that, according to the premise of this story, carries 33 billion tons, about 3.3 plus 10^13 kilograms. A mass that would normally announce itself through size and brightness, but instead sits in our models like a hidden constant. If the core is that heavy and yet appears visually small, then it must be either extremely dark, extremely dense, or both. And if it is extremely dark, then the absence of reflectivity begins to feel intentional, like stealth that is not about invisibility, but about boredom. Give the telescopes nothing to latch onto. Dr. Avi Loeb has often emphasized that we should treat anomalies with a kind of humility. Sometimes the universe is stranger than our categories. Sometimes our models are incomplete. But sometimes the simplest explanation is that we are looking at something designed. The word designed does not have to mean hostile. It only means shaped by goals. Dr. Michio Kaku's broader theme, the one that quietly returns in interviews and lectures, is that advanced technology might be indistinguishable from natural processes to a casual glance, especially if it wants to be. A type win. A civilization does not need to parade its machinery. It can hide it inside the very environments we already expect to be complicated. Dust, plasma, magnetic noise, cosmic clutter. So when the shell peels off, it is not only a visual change, it is a narrative change. It says, the phase of passing is over. The phase of waiting has begun. At L1, everything is upstream and always monitored, and that makes the stillness feel less like drifting and more like posture. There is a quieter possibility, grounded enough to stay in the room with us. Perhaps the shell is not camouflage, but shielding, a sacrificial layer meant to take the brunt of radiation and micrometeoroid damage during the interstellar crossing. Once in our system, close to the sun, the layer becomes unstable or unnecessary, and it is released. Either way, the meaning is similar. The object changes configuration when it arrives, and configuration changes are the language of machines. Now we allow one imaginative leap, but we do it in a whisper. Imagine that the dust and fragments were not random at all. Imagine they were arranged loosely as a distributed sensor net, a disposable swarm that samples the solar wind, the radio environment, the chemical makeup of our exosphere, then falls away once the core reaches its intended perch. A net that is thrown, gathers data, and is then discarded like fishing line cut free. Whether that leap is true or not, the physics remains. The core is what matters now, a black, cold object hanging near Earth-Sun L1, heavy enough to tilt the calculations of LAGEOS-2, quiet enough that the Deep Space Network has to argue with itself about what it is seeing. And if the shell has peeled away, then the next question is almost tender in its simplicity. What is the shape underneath? Because shape is purpose made visible. A rock has no reason to be elegant. A device often does. In the next chapter, we follow the shape implied by orbit and mass and ask whether the core is more like a vessel, an ark ship, or something narrower and more pointed. A lander, a drill, a tool built to meet an atmosphere as if it has done so before. In the folder labeled 3I Atlas, there is a word that feels too deliberate to be accidental. Not fragment, not core, lander. It appears once, then again, as if someone tried to bury it under gentler phrasing, but could not quite delete the instinct. Tonight, December 15th in the United States, this story goes public in a calm voice, even as the numbers argue. Deep Space Network tracking implies 3I Atlas shed about 15 kilometers. LAGEOS-2 residuals keep circling back to a mass and estimate that makes your mind go quiet. 33 billion tons, about 3.3 kilometers 13 cows. And the location that keeps showing up in solutions is not a random crossing point, but a perch between Earth and Sun, Lagrange Point L1. Once you accept those anchors, the next mystery is not who built it, but what geometry could make the behavior plausible. Shape is the most honest part of an object. Dust can lie. Reflections can lie. Even a light curve can mislead when a surface is designed to drink sunlight instead of throwing it back. But geometry has to satisfy stress, heat, and momentum, and those three do not negotiate. Dr. Michio Kaku often frames interstellar travel as the art of surviving extremes. Interstellar cold, radiation, micrometeoroid erosion, then the sudden glare and plasma of a star. A device that crosses those regimes does not need to look elegant. It needs to look durable. If the word lander is even partly true, then durability takes on a new meaning, because atmospheres are not gentle. They are a thick, fast-moving fluid that turns velocity into heat. A natural rock entering Earth's atmosphere has one strategy. It falls, it heats, it breaks, and it either burns away or reaches the ground in pieces. Even modest meteoroids can release shocking energy because kinetic energy scales with the square of velocity. If you attach the mass estimate, 3.3 plus 10, so 13 cols, to an uncontrolled entry, the result stops being a meteor and becomes a planetary event. But the file does not describe a plunge. It describes a break, then a pause, then a stillness near Lagrange Point L1, the kind of staging perch that makes an impact story feel like the wrong genre. That leads to the first grounded speculation, the one that keeps the story from collapsing into a single, catastrophic picture. 3I Atlas may not be the lander at all. It may be the carrier, the scaffold, the parked platform. The lander could be a smaller component nested inside the cold core, protected by the same heavy architecture that LAGEOS-2 seems to weigh from a distance. In that interpretation, the large mass is not meant to meet the atmosphere. It is meant to bring something else close enough, with choice instead of collision. Dr. Avi Loeb's habit of thinking helps here. Start with the simplest engineered logic. If you want to deliver a payload to a planet, you do not throw your entire interstellar carrier into air. You release a capsule, you shed a module, you separate stages. We do this because atmospheric entry is a carefully budgeted trade between heat, deceleration, and accuracy. A visitor that can manage a 15 km delta wave does not need to gamble on a chaotic impact when it can choose a controlled release. So why does the file flirt with a second word, one that feels sharper? Drill. In aerospace, blunt bodies spread heat and reduce peak heating, but they slow violently and experience crushing deceleration. Slender, pointed bodies keep a high ballistic coefficient. They resist deceleration and penetrate deeper before shedding energy. A drill shape is not a melodrama. It is a design decision for passing through gas, as if the gas is only a thin veil. Mass and cross-section matter in a way that feels almost like a secret. A dense object with a small frontal area loses speed more slowly in an atmosphere. It punches deeper. That is why some natural iron meteoroids reach the surface, while fragile, porous bodies fragment high above it. If an engineered lander were built to reach the ground, or to reach deep atmosphere, you would expect it to be dense, heat-tolerant, and shaped to manage shock waves without tearing itself apart. But the summary uses another image that points in the opposite direction. Ark ship. An ark ship implies volume, insulation, internal stability, maybe even the long, patient care of something preserved. That sounds incompatible with a drill until you remember how engineers hide delicate things inside brutal shells. A penetrator can be the outer geometry, while the interior is a protected chamber. A black, cold core can be a vault. The outside is built for violence. The inside is built for quiet. This is where Dr. Michio Kaku's Kardashev framing becomes more than a label. If a civilization can hold a 33 billion ton mass near Lagrange Point L1, then its engineering margins are not the margins we live with. It can afford thickness. It can afford layered shielding. It can afford redundancy so deep it looks geological. For such a builder, a lander could be overbuilt the way we overbuild bridges, except on a scale where the bridge is also a fortress. The waiting posture makes timing part of the geometry. The file keeps a soft calendar, a hint that an alignment window matters. Not because alignments are mystical, but because alignments simplify trajectories and communication. From Lagrange Point L1, a release can be tuned to intersect Earth's neighborhood with minimal correction, like letting a marble roll off a ridge into a valley. In orbital mechanics, small nudges at the right place can create large changes downstream, and patience turns those nudges into a path that looks like fate from the ground. Now we allow one imaginative leap, offered softly and then set back down. Imagine a narrow module separating from 3i Atlas without flare or sound, sliding away like a dark seed released into a river. It does not fall fast at first. It drifts, almost lazily, until geometry turns drift into approach. And on the night it finally meets air, it does not blaze like a meteor. It arrives wrapped in its own control, shaping the shock and heat as if the atmosphere is a material it already understands. Then the calm voice returns to what we can actually hold. We do not know the true shape. We do not know whether lander is a literal term or a nervous metaphor in an engineer's notes. We only know the constraints that keep repeating. Deep space network tracking suggesting a 15 kilomolars slowdown, LAGEOS-2 implying about 3.3 bars 10 to the 13 cols, and a mass that appears to be holding near Lagrange Point L1 rather than passing through. So we end this chapter with a single question placed softly on the table and left there. If 3I Atlas is not a falling rock, but a parked platform with a hidden lander, what does that lander need most? Heat protection, guidance, or an inner warmth stable enough to carry something fragile through the cold between stars? Tonight, the object looks cold from a distance. That is what the telescopes suggest, a black surface swallowing sunlight, hanging near the Earth-Sun balance point. But the thermal notes in the file do not match the image. They read like a quiet contradiction. If 3I Atlas is truly parked near Lagrange Point L1, then something inside it may be warmer than it has any right to be. The same anchors remain steady. Deep space network tracking implies a deceleration of about 15 kilometers per second. LAGEOS-2 residuals keep pointing toward a mass near 33 billion tons, about 3.3 kilobars 10 to 13 kilograms. Those facts do not tell us what the interior holds, but they do tell us what the interior can afford. A massive body can carry thick shielding, deep insulation, and heat storage on scales that make ordinary spacecraft design feel small. In ordinary astronomy, internal heat in small bodies has familiar sources. Long-lived radioactive isotopes can warm a rocky interior, slowly and weakly, over billions of years. Sunlight can heat a surface, then the warmth can creep inward by conduction. Impacts can flash heat into fractures and pockets. But those explanations usually produce gradients that fade with time and distance. They do not create a stable, maintained temperature floor once an object changes its environment. So the file's thermal behavior becomes the next puzzle piece. The notes describe a surface signature that is muted, as if the skin is very cold or very reluctant to radiate, and yet there is a persistent component that does not drop the way a passive rock should. The wording is cautious, the kind of language official briefings use when they do not want anyone sprinting ahead of the data, consistent with an internal source, requires additional observations. One physical loophole is emissivity. If the surface is engineered to radiate poorly in the infrared, then even a warmer interior can look dull. Low emissivity skins, multi-layer insulation, and phase change thermal buffers can flatten temperature swings into a steady floor. None of this requires exotic matter. It requires design. Dr. Michio Kaku often reminds audiences that interstellar travel is not only about crossing distance, but about surviving extremes. Radiation, micrometeoroids, and deep cold are not background conditions. They are the main event. If a builder wanted a payload to arrive intact after decades or centuries, the simplest requirement would be temperature stability. Chemistry, electronics, and especially biology all prefer a narrow band. Extreme cold can be tolerated, but it slows reactions, embrittles materials, and turns awakening into a risk. Dr. Avi Loeb's approach invites a practical question. If an object behaves as if it can break and hold position, then it likely has access to power. Power systems produce waste heat. Even the cleanest system leaks warmth because entropy has patience. A small probe might hide its heat by radiating gently over a wide area. A large carrier might hide it by insulating the source and letting only a controlled fraction escape, tuning what an infrared instrument can infer at a distance. There is another grounded possibility that sounds almost too simple. The interior could be warm because it was made warm before arrival, then sealed like a thermos. With enough mass and insulation, stored heat can last a long time. The core could be thick metal and composite, a thermal flywheel. It could coast, not only in motion, but in temperature. When 3I Atlas breaks and parks near Lagrange Point L1, it is not turning on. It is revealing that it never fully turned off. But the file hints that the warmth is not merely residual. The phrase steady output appears beside the plotted estimates, and that nudges the mind toward active maintenance. Radioisotope sources are real, but if the maintained temperature is high enough and long enough, then the implied power could be substantial. Chemical batteries do not last that long without slow loss. Solar power is abundant near the sun, but collection can be hidden, folded, or internal, especially if the exterior is built to be visually uninteresting and thermally disciplined. Here, the story slips into its hypothetical nightmare rhythm: soft voice, sharp edge. A cold black core at Lagrange Point L1, heavy enough to tug on our models, still and silent, yet warm within. If the interior is being kept above a threshold, then something inside benefits from that warmth. It could be propellant management, keeping fluids and mechanisms usable. It could be computation, electronics held in a stable range to avoid brittleness and failure. Or it could be preservation, a cargo that does not like vacuum cold. Imagine one quiet image, then let it go. Inside the dark core of 3I Atlas, behind layers of shielding and structure, there is a chamber where temperature does not follow the stars. The outside skin stays cold enough to look inert. The inside remains in a narrow band, like a cradle held far from noise. The mechanism does not have to be dramatic. It could be slow decay heat. It could be a compact reactor running at low power. It could be something we do not recognize. The only claim the file dares to lean on is this: the interior is not cooling the way a passive body would. A skeptical reader would ask for the simplest reason before accepting the unsettling one. Infrared inference is hard. You estimate temperature from emitted radiation, and that depends on emissivity, surface roughness, rotation, and viewing geometry. A low emissivity surface can look colder than it is. A rapidly rotating body can smear hot and cold regions into an average that hides detail. If the shell recently peeled away, then the surface composition may have changed quickly, and our assumptions may lag behind reality. And yet, even skepticism has a boundary. If repeated observations over multiple times and angles keep requiring an internal component, then the thermal story becomes as stubborn as the mass story. It does not prove intention, but it makes certain kinds of intention more plausible. A parked object near Lagrange Point L1 with an internal heat signature that does not fade looks less like a dead fragment and more like a system that expects to remain functional. This is also where the lander idea tightens. If a smaller module is nested inside, a warm interior could be preparation. Systems that deploy need to be ready. Valves need to open, mechanisms need to move, sensors need to wake. A warm vault is a vault that can act on schedule, and schedules bring us back to the quiet calendar drifting through the file, the sense that geometry and timing matter, not as omen, but as logistics. So we end with a question that is easy to keep and hard to answer. If 3I Atlas is warm inside, while it waits at Lagrange Point L1. Is that warmth a byproduct of power, or is it a promise that something inside is meant to awaken near Earth? In the next chapter, we listen for the gentlest consequence of all, gravity's whisper, and the small tides a silent weight might raise in air and ocean. It is strange how quickly a number can turn into a presence. 33 billion tons is just ink on a screen until you remember it is supposed to be hanging near Earth-Sun L1, and then the air around you feels like it belongs to a larger room. Our planet wears its atmosphere like an ocean turned inside out. It flows, it sloshes, it rises and falls. We talk about tides as if they are only a shoreline story, but the same physics touches the sky. The sun and the moon pull gently on the air, stretching it by a little, then letting it settle again and again in rhythms so familiar that we rarely notice them. If 3I Atlas truly carries about 3.3 13 kilograms and truly holds near Lagrange Point L1, then it also becomes a new tide maker, at least in principle. Gravity does not care whether a mass is natural or engineered. It only cares that it is there. The question is not whether 3I Atlas pulls on Earth. The question is whether the pull is large enough to be heard. In strict physics, distance is merciless. Lagrange Point L1 sits about 1,000,000 miles away, and at that range, even a mountain's worth of mass becomes a whisper. The extra acceleration from 3I Atlas would be so tiny that oceans would not notice, and most instruments would treat it as noise. That is the comforting version, a silent weight that is too far away to touch us. But the file we have been following does not feel comforting. It is built from residuals, those stubborn leftovers that remain after you subtract everything you understand. LAGEOS-2 is already part of this story because millimeters matter to it. If analysts are willing to infer a 33 billion ton mass from orbital drifts, then they will also be willing to search for the faintest periodic signatures on Earth, not in waves you can see, but in pressure, density, and timing. Atmospheric tides are subtle, even when the sun drives them. They show up as gentle patterns in pressure, in the height of the upper atmosphere, in the way satellites experience drag that rises and falls with the daily cycle. Engineers who track low-orbit spacecraft already live with this. The atmosphere swells when it is heated, then relaxes. If you are listening for a new hand on the system, you start by asking whether the swelling has acquired a new rhythm. The declassified style notes in our file describe a search for correlation. When 3I Atlas appears to settle near Lagrange Point L1, do the upper atmosphere models get a little worse in a specific direction? Do tiny timing errors in radio links cluster when the Earth, the Sun, and 3I Atlas line up? Do space weather sensors show a recurring ripple that is not solar, not lunar, not seasonal, the kind of work no one celebrates because the result is either nothing or it is a sentence that forces a new muddle and a new pointing schedule for the deep space network? Dr. Avi Loeb's insistence on testing simple technological explanations invites a second possibility. What if the tide is not gravitational at all? What if it is induced, a massive object near L1 that can interact with the solar wind and magnetic fields could also couple, indirectly, to Earth's magnetosphere and ionosphere, not by yanking the air with gravity, but by nudging charged layers with fields and currents, which then hand energy down to neutral air as heat and motion. Dr. Michio Kaku's Type Y framing makes that idea feel less like fantasy and more like a scaled-up version of what we already know. We already disturb the ionosphere with our own transmissions, weekly and locally. We already watch geomagnetic storms push currents through the sky, raising and lowering densities in the thermosphere. A system that can break 3I Atlas by 15 kilometers might be able to do a quieter thing too, the cosmic equivalent of plucking a string, then listening to how Earth rings. Here is the image, offered gently. Imagine the upper atmosphere as a thin drumhead stretched around the planet. The sun taps it every day with heat. The moon and the sun pull on it with gravity. And then, from the direction of Lagrange Point L1, something adds a new tap, so soft that you only notice when you replay the recording and see the waveform repeat. If such a tap exists, it would not have to be loud to be informative. A tiny, repeated modulation could map how our atmosphere responds, how it couples to our magnetic field, how quickly disturbances travel. It could be a calibration pulse. It could be a form of radar that uses the planet's own envelope as the target. It could be a test that tells 3I Atlas when the air is calm enough or charged enough for whatever comes next. Skepticism still belongs in the room with us. The atmosphere is complicated. Solar activity changes hour by hour. Volcanic aerosols, seasonal winds, and ordinary geomagnetic storms can mimic patterns if you are searching too hard. Correlation is not control. A new rhythm could be a coincidence that our nervous brains stitch into a story. And yet the calm unease remains because of where the weight is said to be waiting. Lagrange Point L1 is not merely near us. It is upstream of everything the sun sends. If 3I Atlas is holding there, it has access to a constant stream of light and plasma and a clean line for watching Earth's response. It can wait without blinking. In 3 days, December 19th sits on the calendar like a quiet hinge. Alignment windows are not mystical, but they are useful. They simplify geometry. They sharpen lines. They make small forces matter. If someone were timing a release, a signal, or a final adjustment from 3I Atlas, you would expect it to prefer a night when the system's angles become simple. So tonight, as this file becomes a story you can fall asleep to, hold one question as lightly as possible. If the atmosphere is already a moving, breathing ocean, and if 3I Atlas is truly parked where it can listen to every ripple, then are these faint tides just physics, or are they the first gentle knock from something that has been waiting to be answered? 3 days is a small number in astronomy, but it is a serious number in planning. In the file, one date repeats with quiet insistence, December 19th. Tonight, December 15th, as this video goes public in the United States, 3I Atlas is still described as parked near Earth-Sun Lagrange Point L1, still linked to the same anchors that started the rumor storm, a deep space network track implying about 15 kilometers of deceleration, and LAGEOS-2 residuals that keep pulling the mass estimate back toward 33 billion tons, about 3.3 what's to was 13 kilograms. The strange part is not that analysts notice a date. Every mission lives by dates. The strange part is that this date appears in a story that began with an object that should not be able to schedule anything at all. A natural fragment does not pick a window. It arrives when gravity allows. It does not wait for a calendar. If you have ever watched orbital mechanics up close, you know why dates matter. Space travel is not only about speed, it is about timing small actions when geometry makes them powerful. At L1, a tiny change can open a long corridor. A gentle push can turn a hover into an approach, or turn an approach into a clean miss. A system that holds at L1 is already sitting on a hinge. Dr. Michio Kaku often frames advanced technology as the ability to control not only energy, but sequence. A Type 1 capable system is not impressed by brute force. It prefers leverage. Dr. Avi Loeb's arguments about anomalous visitors lean in the same direction. If you ever encounter a probe, it will not act like a meteor. It will act like a patient instrument, doing the minimum it needs to do, exactly when it needs to do it. So why December 19th? The conservative answer is that it could be nothing more than our own scheduling. Deep space network time, antenna handoffs, calibration cycles, a planned observation campaign with a neat marker on a shared calendar. Sometimes the date in the story is not the date in the sky. It is the date in our paperwork. But the folder is not shaped like paperwork. It reads like anticipation. The notes cluster around the idea of a geometry window, the kind of phrase you use when a certain alignment of angles makes a task easier. 3 days from now is close to the December solstice, when Earth's orientation relative to the Sun reaches an extreme. For ordinary life, that is a seasonal line in the sand. For magnetic and plasma interactions, it is another shift in angle, another change in how Earth's magnetosphere presents itself to the solar wind. If 3I Atlas can couple to plasma and fields, as the earlier chapters quietly suggest, then Earth's magnetic posture might matter, not as mysticism, but as impedance matching. How efficiently can a system lean on the solar wind? How cleanly can it shape a wake? How stable is the corridor it creates? A slight change in geometry can turn a noisy environment into a readable one. And if the earlier hint about atmospheric tides is even partly true, then December 19th could be the moment the test becomes an action. A few days of observation can map the background. It can learn the daily breathing of our upper atmosphere, the pattern of radio leakage across the night side, the way solar wind changes propagate through our field lines. Then, on the chosen night, the system can do one clear thing and measure the response. The second grounded speculation in the file is simpler and colder. December 19th might be the best low-energy departure window from L1 for something small. A nested module, a capsule, a lander, whatever word you prefer, could be released with almost no drama, then allowed to drift along a pre-selected path that intersects Earth's space with minimal correction. In that scenario, 3I Atlas does not attack. It does not arrive. It merely opens its hand and lets physics carry a package forward. Here is one imaginative image, offered softly and then put away. Picture the black core near L1, perfectly quiet. Around it, no dust now, no swarm, only a disciplined shape. At some point in the night of December 19th, a smaller dark form separates, not fast, not bright, just slipping free, like a seed released into a slow current. For hours, it looks like nothing. Then later, it becomes a new dot on a new plot, and someone at a console stops speaking. We should also admit the simplest, most human possibility. December 19th could be the date we chose to fear because fear likes neat numbers and short countdowns. 3 days feels like a fuse. It fits the mind's appetite for narrative. But the universe does not care about our appetite, and a Type 1 capable system, if this story is even close to true, would care even less. Still, the date remains, and the location remains, and the mass remains. 33 billion tons does not need to move quickly to matter. It can wait at Earth-Sun Lagrange Point L1 and make us spend our attention. It can let our instruments do the work of announcing it, while it keeps the advantage of silence. So as we move closer to December 19th, the calm question becomes more precise. If 3i Atlas is holding position with purpose, what is the purpose of waiting for a specific night? A better line of sight, a cleaner magnetic angle, a release window, or a moment when we are all tired enough to mistake preparation for coincidence. In the final chapter, we return to the simplest fact that never changes. The object does not speak. It hangs heavy and quiet, and the quiet itself begins to feel like a kind of message. By the time you hear this, it is still December 15th in the United States, and there are 3 nights left before December 19th. 3 nights for the mind to spin stories, and 3 nights for the sky to remain indifferent. The file we have followed begins with motion and ends with stillness. Deep Space Network, tracking that implies 3i Atlas shed about 15 kilomolars. LAGEOS-2 residuals that keep insisting on a mass near 33 billion tons, about 3.3 bars 10 or 13 kilograms, and a location that feels like a deliberate perch, Earth-Sun Lagrange Point L1. Upstream of our planet, inside the same corridor our own monitors use to watch the sun. In the hypothetical nightmare rhythm, the fear does not come from explosions. It comes from scale and quiet. A mountain's worth of mass, hanging where it can see both the sun and earth, not falling, not fleeing, not flickering with comet light, just waiting. Dr. Michio Kaku's voice, in the background of this whole story, is not a prophecy, but a criterion. Delta V, the ability to change momentum. Nature does not break. That idea is not a conspiracy. It is a reminder that a sudden, purposeful change in motion is one of the clearest fingerprints of engineering. If 3i Atlas truly performed a braking maneuver and then held near L1, the clearest claim we can make is also the smallest one. The behavior resembles control. Dr. Avi Loeb's contribution is the permission to consider that resemblance without turning it into theater. Ask what minimal technology could produce the observed signatures. A sail that leans on light, a magnetic system that leans on plasma, long-time scales that keep forces gentle, a configuration change where a shell peels away, leaving a darker, more disciplined core. These ideas are still speculation, but they are speculation with physics under them, like a floor you can feel even in the dark. Now the story widens into the last phase, the wind down, where the listener is allowed to feel small without feeling unsafe. Because even in the most unsettling reading, we are still only witnesses. We are not at the center. We are not the engines. We are the observers looking up from a world that keeps turning. If 3i Atlas is truly at Lagrange Point L1, it is far enough away that it cannot reach out like a hand. The gravitational whisper it adds is tiny at Earth's surface. The sunlight we receive is still the sun's. The air you are breathing is still your planet's. The immediate night does not change. The fear, if you feel it, lives in the mind's future tense, and future tense is always where we lose sleep. So let the tense soften. Tonight, it is simply there, a dark weight in a bright corridor, a new variable in our models, a silent object that forces us to measure, because measurement is what we do when we cannot control. If it is real, the Deep Space Network keeps tracking it. If it is real, the analysts keep refining those residuals. If it is real, then somewhere in a lab or an office, Someone keeps subtracting known forces and finding that a little something remains. One of the gentlest forms of cosmic horror is the realization that silence can be strategic. We tend to associate power with noise, engines, signals, light. But a more advanced system might do the opposite. It might conserve energy. It might reduce emissions. It might wait for geometry. It might let the watched announce the watcher, because the watched are the ones who cannot stop looking. If the date December 19th matters, it will matter in a practical way. A cleaner line of sight, a simpler trajectory, a magnetic posture that makes coupling easier, a release window for something smaller, something nested, something that has been kept warm inside the cold core, or it might matter only to us, because countdowns make fear feel organized. Either way, the same thought returns, steady as breathing. A 33 billion ton presence at Earth-Sun Lagrange Point L1 is not a meteor. It is not an accident. It is, at minimum, a puzzle that refuses to leave. And puzzles have a strange gift. They make us honest about what we do not know. So as you let your eyes grow heavy, you can hold a comforting truth alongside the unsettling one. We have lived under a sky full of unknowns for all of human history, and the sky did not need our permission to be strange. The stars were always silent. The comets were always unpredictable. The universe has always carried objects we have not named yet. If 3I Atlas is a natural fragment, then the story ends with a reminder that nature can still surprise us and that our models are not finished. If 3I Atlas is engineered, then the story ends with a different reminder that even an immense capability can choose patience over violence, observation over spectacle, stillness over drama. Either way, tonight is still yours. Let the thought of the silent watcher become less like a threat and more like a horizon. Something distant, something real or not real, something the instruments will keep discussing while you rest. You do not have to solve it in bed. You only have to listen to the calmness of the room and the steady, ordinary gravity holding you and the soft, familiar fact that the earth is still turning. And somewhere, near the line between our world and the sun, 3I Atlas hangs in quiet balance, heavy enough to bend equations, quiet enough to let your breath be the loudest thing you hear.